Construction of Donryu Pump Station. In this video, we will introduce the construction of underground pump station to protect the city of Kyoto from flooding, as well as the pneumatic caisson method applied for its construction. This video includes background of this project, outline of this project, characteristics of the pneumatic caisson method, construction process, and new initiatives. The Iroha-Donryu Tunnel covers parts of Kyoto City, Mukou City, and Nagaoka-kyo City in Kyoto Prefecture, and the Donryu Pump Station is located and served at the end of the downstream. This area has been developing rapid urbanization since the high economic growth period, with well-developed transportation networks such as the Hankyu-Kyoto Line, the JR Tokaido Main Line, and National Road No. 171. This area is located in a bowl-shaped terrain with poor drainage, sandwiched between the first-class rivers, Wata River and Katsura River. The main drainage channels, Terada River and Ishida River, were originally developed as artificial irrigation waterways. Due to the presence of houses along riversides and numerous railway and road bridges, widening rivers has been difficult. As a result, a significant issue was flooding in approximately 500 households after heavy rainfall. Along Prefecture Road, Fushimi-Muko Line, Maeda Underpass often experienced road closures due to flooding caused by adjacent Ishida River overflowing during heavy rains. To address these flooding issues, construction of Iroha-Donryu Tunnel began as part of the rainwater countermeasures project in the right bank area of Katsura River. After city plan for construction of the Iroha-Donryu Tunnel was approved in December 1995, construction work of North Main Line No. 1 rainwater conduit was started in December 1996. In June 2001, North Main Line No. 1 rainwater conduit started the operation, capable of holding 54,000 cubic meters of rainwater, equivalent to 180 of 25-meter swimming pools. After commencement of the operation of North Main Line No. 2 and No. 3 rainwater conduit in October 2011, rainwater storage capacity increased to 107,000 cubic meters, equivalent to 350 of 25-meter swimming pools. Furthermore, since the Donryu Pump Station was provisionally started the operation in March 2022, the capacity of rainwater storage increased to 196,450 cubic meters, equivalent to 650 of 25-meter swimming pools. Then, by completion of the regulating reservoir in the fiscal year of 2023, maximum capacity will increase to 238,200 cubic meters, equivalent to about 800 of 25-meter swimming pools. As a result, this made possible to prevent almost all of serious flooding that affected up to 800 households in the fiscal year of 1990. The Donryu Pump Station is located at the end of downstream of the Iroha-Donryu Tunnel. It serves as a pumping station to discharge rainwater stored inside the tunnel at capacity of 148,000 cubic meters into Katsura River at the rate of 10 cubic meters per second. This discharging rate of 10 cubic meters per second is equivalent to emptying a 25-meter swimming pool in approximately 30 seconds. This project involves construction of a vast underground space to install drainage pumps, which serve as heart of the Donryu Pump Station. Underground space is 39.5 meters by 42.5 meters and reaches to 37 meters depth. This size is large enough to accommodate approximately up to the third floor of the Kyoto Tower building. To create the vast underground space, the pneumatic caisson method was applied for this project. The pneumatic caisson method is a technology introduced from the United States for the reconstruction work after the Great Kanto earthquake. Pneumatic caisson means an air chamber. It applies principle of preventing water infiltration by using air pressure like a cup upside down holding air inside in the water. Reinforced concrete chamber is constructed on the ground, and an air-tightened working chamber is provided at the bottom of caisson structure. Compressed air matching underground water pressure is sent into this working chamber to prevent water infiltration, allowing caisson structure to be sunk into the ground by carrying out excavation and soil removal inside working chamber. Currently, this method is widely applied for various purposes such as foundations for bridges and buildings, launching and arrival shafts for shield tunnels, underground railways and roads, and underground storage facilities. Next, we will explain the reasons this construction method was selected. One significant reason for application of the pneumatic caisson method for this project is the advantage of not requiring retaining walls. When applying open-cut excavation methods, earth-retaining walls like diaphragm wall method are required for 40 meters excavation. However, for ground conditions for this project, the soil at the bottom surface of excavation was gravelly, which may not hold caisson structure. Additionally, one of the important reasons was that shortening construction schedule was requested to expedite the operation of this pump station. Therefore, the pneumatic caisson method, which does not require construction of earth-retaining walls, was selected. Next, let us explain an actual construction workflow of the pneumatic caisson method. The construction workflow of the pneumatic caisson method may be broadly divided into 4 stages: cutting-edge installation work, sinking and excavation work, structure construction work, and concrete filling work into working chamber. The first step is cutting-edge installation work, which installs cutting-edge section on the ground to be required to sink caisson structure into the ground. To reduce the effect on the surrounding ground, protective steel sheet piles shall be driven into the ground around caisson structure. Following that, excavation work inside steel sheet piles shall be conducted. Next, we create a sand center to support roof slab of working chamber. Next, installation of supporting plate. By installing wooden plate called supporting plate at cutting edge contact area, it prevents cutting edge from sinking into the ground by self-weight. After installation of supporting plate is completed, steel-made cutting edges fabricated in factory are transported and installed. Since cutting edge components are manufactured by sections, they are integrated together by welding. Once diagonal steel plates are installed, entire form of cutting-edge section, which may gradually sink into the ground by self-weight, shall be visible.
Next, secondary embankment shall be conducted, followed by the installation of roof slab steel plates to complete construction of entire working chamber. Seating rails for caisson shovels shall be installed to allow caisson shovels, a specialized heavy machinery for excavation, to travel in working chamber. Once roof slab steel plates are installed and scaffoldings are installed surrounding entire caisson structure, final step is to cast concrete. Cutting-edge installation work is completed. Next is the structure construction work. In the pneumatic caisson method, caisson structure is constructed by section of 3 to 4.5 meters as one lot according to sinking and excavation work. At this project, caisson structure up to second lot was constructed on the ground before sinking and excavation work began. Following this, we move on to installation of precast suspended girders. These girders work a crucial role in supporting roof slab of expansive working chamber, which is approximately 40 meters span and ensuring structural integrity of working chamber. The next step is sinking and excavation work. First, excavation work, which is called opening excavation, shall be conducted to remove sand center that supported roof slab of working chamber. To excavate in narrow space, small electric excavators shall be used. Once opening ratio is increased till exposed ceiling rails, roof traveling heavy machinery, caisson shovel shall be installed and excavation work is continued. When opening ratio is increased, caisson structure itself shall gradually sink into the ground by self-weight. Excavated soils are loaded into earth bucket and transported to the surface through material shafts. As deeper excavation depth, manned operations inside pressured environment of working chamber shall be difficult to keep work efficiency due to working hour restrictions. To address this, remote-controlled excavation of caisson shovel is applied by controlling caisson shovels from remote control room on the ground. According to camera feeding installed on caisson shovel operators may control safe and effectively regardless of excavation depth. Remote control room shall be equipped with same number of remote control excavation units as caisson shovels. Caisson shovel operators shall continue excavation work with cooperation each other. Furthermore, real-time data sent from various sensors installed on caisson structure shall be gathered in remote control room. Sinking and excavation work shall be controlled carefully by our engineers based on receiving data. In the pneumatic caisson method, sinking and excavation work and structure construction work are repeated under precise control. As a result, the entire building gradually sinks into the ground, and a vast underground structure shall be constructed. After completion of sinking of caisson structure, ground bearing capacity tests shall be conducted. This test is conducted to verify whether ground has sufficient bearing capacity to support caisson structure. This is one of the advantages of the pneumatic caisson method, to have bearing capacity test directly on bottom surface of excavation. The final step after completion of ground bearing capacity test is concrete filling work into working chamber. Once all equipments inside working chamber are removed, entire working chamber shall be filled with concrete through concrete injection pipes. After curing concrete and removing suspension girders, underground section of the Donryu Pump Station shall be completed. In this project of the Donryu Pump Station, unprecedented initiatives by new technologies has been implemented. These include precast suspended girders and caisson shovel automated operation system. Let's start with the introduction of precast suspended girders. Working chamber for sinking and excavation work requires suspended girder structure to support its vast ceiling, approximately 40 meter span, and to ensure rigidity of structure. However, on-site fabrication of suspended girders would require a certain construction period to fabricate. To address this challenge and meet demand for early operation of this pump station, precast suspended girders were applied. By utilizing precast concrete suspended girder components fabricated in factory, this contributed to improve construction work accuracy and shorten construction period. This approach represents new trial and unique to this project, which was not previously applied in conventional pneumatic caisson construction projects. Next, we will introduce caisson shovel automated operation system. Currently, excavation work in working chamber is conducted by remote control of caisson shovels inside working chamber from remote control room on the ground. With 11 caisson shovels in operation for this project, 11 operators are required for each caisson shovel. However, recently in Japan, shortage of caisson shovel operators in future shall be concerned due to decline of working population. Therefore, in this project, we conducted on-site demonstration tests of caisson shovel automated operation system. In this test, 6 caisson shovels were automatically and simultaneously operated and successfully transported soils by automated operation. This on-site test was a part of project under Construction Technology Development Grant Program of Ministry of Land, Infrastructure, Transport and Tourism in the fiscal year 2018. This was a collaborative effort between industry, local, municipal and university aimed at addressing social issues such as aging population and declining workforce through cutting-edge technology development. This initiative was realized through the collaboration and cooperation between Oriental Shiraishi Corporation, Kyoto Prefecture, and Chiba Institute of Technology as co-parties and many stakeholders. Kyoto has suffered from flooding for centuries. However, Katsura River right bank drainage project shall be overcoming this challenge, which has been existed for more than hundreds of years. The Iroha-Donryu Tunnel lies deep underground, invisible to public eyes, yet it continues to protect the city of Kyoto from flooding to this day.